From the MIT Energy Initiative, this is What If It Works, looking at the energy solutions for climate change. I'm Tara Miller.
And I'm Rob Stoner.
And today, the tricky but vital task of decarbonizing all sorts of hidden processes, things you probably never think about. So not the flashy stuff, like cars and airplanes, which are the polluters we worry a lot about and talk a lot about.
But there's all these hidden things that are around us that are the stuff that makes up our world, that make up the food we eat, the pharmaceuticals we make, the chemicals and materials that are around us, the materials we use to build our built world. Those are also extraordinarily carbon intensive. They lead to huge amount of emissions that arise from the production of those materials.
That's Yogi Surendranath, a professor of chemistry and chemical engineering at MIT. And he says, take something like steel, which is probably an integral part of most offices that you've worked in or most schools that you've attended.
We make enormous quantities of steel around the world. We build literally skyscrapers with steel. Every single atom in that steel corresponds to a certain number of molecules of CO2 that were emitted to make that.
So as buildings get taller and people increasingly move from the countryside to the city, we have to figure out, how do we accommodate all these people and get rid of or reduce the carbon-intensive processes used to make steel? But if that seems like a big problem, consider what you ate today. Very likely, it benefited from a process called Haber-Bosch, which is named after two German chemists. And for about the last century, it has been helping to create huge amounts of fertilizer that makes farmland around the world much more productive, and that helps feed the 8 billion people on this planet. If you're chemically inclined, here's Yogi giving a quick explanation of Haber-Bosch.
It's a process that's been heavily optimized in industry, but the crux of it is pretty simple, at least at an atomistic level, which is you're taking nitrogen from the air and you're combining it with hydrogen that you source from fossil fuels, and you're combining that nitrogen and hydrogen to make ammonia. And ammonia is the key component in most fertilizers. So even in our bodies, there's food that we eat that has a huge carbon footprint to it. And even that amount, that value, just making the ammonia we use to grow all the food that we do in the world, that is already about a single percent of the entire energy budget of the planet.
So if we're going to tackle climate change, we have to do something about the processes to make steel and fertilizer and plastics and concrete, and on it goes. Basically, it's all that stuff that makes the world modern and which generates something like a quarter of our carbon dioxide emissions.
Industrialization emerged out of the ready availability and the growth and development of large ability to extract fossil reserves of energy. So when we were able to extract a large amount of that fossil energy, it spawned a huge panoply of industries underneath it that use that energy storehouse, that sort of historical, geological storehouse of energy, and cashed out that energy to make all the things that we have in the stuff of our world, right? And to really achieve deep decarbonization, we have to not only do the decarbonization of, what turns on the lights and what heats our homes and what powers our cars, but also all these other industrial processes, because they make a huge fraction of the overall carbon budget of the planet.
But as you can imagine, there are complications. So go back to that Haber-Bosch process, which provides us with so much fertilizer, and in turn provides us with so much food. Yogi says we're awfully good at making that fertilizer using fossil fuels.
We have, over the better part of the last 60 or 80 years, really, really heavily optimized how we make ammonia. So much so that it costs many, many billions of dollars, tens of billions in some cases, to build a new ammonia plant. So much so that the return on investment is actually only after decades of sort of time, right? And so simply changing that entire infrastructure to port in a new chemical feedstock, new feed, is not trivial.
So scientists have a couple of choices, and neither of them is easy. They can try to fiddle with existing effective processes to make them more fuel efficient, or they can throw them out and say, look, there is a better, more sustainable way here. Let's do this other thing. Here is Yogi in conversation with me and Rob.
But I'm not presenting any of this to say that it's daunting. It's just to say that we need to be cognizant of the fact that there's still a lot of new science and new technology that needs to be developed to fully appreciate what it means to, for lack of a better term, transform a large portion of our industrial sector. Right, that's not going to happen overnight. And just like our current industrial sector really developed over many, many decades of development with fossil fuels as the input, there's going to be years and decades of development to be able to transition that, right? But if you look at, for example, how far we've come in even just the primary generation of renewable electricity in the context of solar and wind, if you had looked a decade earlier or 15 years earlier, that too would have seemed daunting. Right? And if you think about where we are, and let's take just one technology that's going to be really, really enabling for the future, which is just water electrolysis, splitting water into hydrogen and oxygen. And of course, there are huge, and we work on a lot of this in our own lab, technological advancements that need to be made to be able to take those technologies to scale. But that mountain we have to climb there is kind of on the order of the type of mountain we climbed over the last 15 years when it came to the cost of solar and the scale at which we've built out solar. And that doesn't mean there aren't still many challenges to climb, but I am very optimistic that we will be able to get there.
I have another question kind of for both of you, because it's kind of like a science/policy question. You know, we're talking about this mountain to climb, and you were saying like solar and wind, they really have climbed a lot of it over the last 10 or 15 years. Is this switch to using chemical processes that are greener, that don't emit as much CO2, is this mostly an issue of we know the chemistry, we just don't have the money, or we don't really know the chemistry, but people are willing to cough up the money? You know what I mean? Is this like a policy thing or like a resource thing? Or is this like we haven't figured it out in the lab yet? We'll let you know.
I think it comes back to, in part, what Yogi was saying before about the scale of these industrial processes and the degree of optimization that we've brought to them, and how replacing them with an alternative that we can imagine, and maybe we can even practice, that has different economics, maybe inferior economics, means we make food more expensive, or we make building materials more expensive. We change the economics of other parts of the economy, and well, there's disruption, and so that's at least a part of it. I
would say that there is absolutely, huge macroeconomic consequences to these transitions, right? But I would just say on the technical side, I think that there's a little bit of a view that things you do in the lab, and then when they get out of the lab, with enough resources, they can then go to scale. And the fact that's really not how most technology development happens. Because what really happens is, what you're really doing in the laboratory is sort of setting the foundation. It's sort of charting a map. The more fine-grained that map is, the faster you'll be able to get to scale. The more, in other words, the more you know of the lay of the land, of the problems you're going to foresee at scale, and how you might be able to avert those is going to allow you to cross that hurdle faster. That's the importance of basic research, even when there's this sort of push to run as fast as we can. Because if you run as fast as you can without a really good map, you might find that after you're $1 billion in and halfway towards your first pilot plant, that you might have a real problem that you don't know how to solve, right? That's why it's really important to make the foundation as solid as you can while we are simultaneously trying to build with what we already know.
The scale of these things, though, and the amount of money and the level of risk also means that I think it's very hard for the private sector to get us there alone. People aren't willing to put billions of dollars into a process that may or may not work. I mean, you're going to borrow that money from a bank. You want it to work. Governments have to be part of it.
Mm-hmm. I think that the points that both of you have made bring up this kind of interesting tension. I don't know how either of you think about it. One is we're in this race. We've got to very quickly try to limit, how much the temperature is raised worldwide. But then on the other hand, as you say, when you think about plastics or fertilizer or steel production, those things didn't happen in like a month or a year. For a long time, people have been thinking, well, you could make plastics a little bit better this way. This doesn't work so well. Let's tweak it. And fertilizer too. And to a point where the production of these things are so good and so rock solid that people might be a little reluctant to be like, oh, here's a totally new process. I know you've totally got this down, but let's do something else. But you have this tension of like, we have got to move really fast, but the other processes got good because what they had on their side is time. I don't know how you reconcile those two things, but they seem to be in a little bit of tension because we kind of don't have time.
You've hit an important nail on the head.
It's a very, very critical piece, right? And I would say it's a little even more than just time. And you hinted upon this. It's just a fear of the unfamiliar. I mean, I can just make the statement even from a almost human capital standpoint, right? A lot of the processes we think about that are going to be really important for these decarbonization goals that use electricity to drive some of these processes, they revolve around this field that we're part of that's known as electrochemistry. Now, if you think about it, that field actually, there aren't many people who know a lot about that, who populate the chemical industries, the ExxonMobils, the Dows, the DuPonts. They're not. And the reason is historically, when you had a large amount of fossil fuels, that was your raw material. You didn't need to use
what's the economic incentive?
What was the economics to hire someone who was trying to do a process that you would only do if you wanted to decarbonize the process? Yet now many of these companies are looking around and saying, gee, we might want to do this, but I don't know how to develop this in-house because I don't even have the people that have expertise in this area.
Electrochemistry has not always been cool.
It's not always.
Now, though, you're at the epicenter of cool chemistry.
I joke about it, but I mean, I think that in many ways, the modern era, and we actually already see this in the cell phones we carry around, right? In many respects, this century will be the century in which that field will play such a central role in addressing some of these problems, but it has not historically been the place where we have trained a lot of our best and brightest and encouraged our best and brightest to go and use this as an enabling science for them to impact the world.
And I shouldn't say, because it'll go to his head, but I mean, Yogi really truly is one of the young leaders in this very, very important resurgence of electrochemistry. And it's our way out of trouble in so many areas.
How do you think about this tension of like moving fast versus what Yogi was saying of like, well, there's like, we have to refine these things?
Well, we're not going to switch off what we have now overnight. And we may even need to intervene in ways that will only be temporary with measures like carbon capture and sequestration. Just keep doing these processes that produce CO2, but capture it. We'll continue producing this way and putting it into the ground. There's a limit in how far we can go. And hopefully new processes will become viable and competitive, and we'll get there, and a transition will occur. And again, government has to be part of it. Big companies are watching.
They're watching.
But they're not doing yet. They're just on the edges of the playing field.
And that other piece is another piece that is important, right? Is that a lot of this has a lot to do with the fact that there is sunk capital, right? If you think about someone who is an ammonia producer that makes fertilizer, they've already spent billions of dollars of capital to build that plant.
Yeah.
Right? And they may not have even gotten a return on investment on that, depending upon when that has been constructed. So asking them to, completely re-engineer that plant or completely scrap it and do something completely different is a very, very big ask, given that sort of stranded capital that's already there in that process, right? And I think that's another place where government and policy can play a strong role to better incentivize how you deal with the sort of inherent, if you will, like head start the legacy processes have simply because they've already have all that invested amount of capital in them.
And we've talked about that before on the show, right? Like I think you talked about, if a coal-fired power plant's being opened in China, yeah, somebody has, let's say, like a mortgage or whatever on that, and they'll be fine if it's open for 30 years, but the government or somebody's going to have to come in and say, let me help you out, because otherwise you're just really in a huge heap of trouble if, like, we only let you run this for 7 years, and then we're like, no, we're shutting it down. Sorry, you can't use it anymore to make money.
So this introduces another very important aspect of the transition, and that is To what degree can we reuse existing facilities, repurpose them, maybe replace part of the Haber-Bosch process with an electrified stage, or the other big process in thermochemistry, the Fischer-Tropsch process, which is the thing you use to make carbon monoxide and hydrogen into hydrocarbons, sort of
fuels. Yeah,
fuels.
Exactly right. But I will say one other key thing that's a piece that's throughout all of this is that, if I go and take a fossil fuel and I use it to power a plant, whether it's Fischer-Tropsch or it's, Haber-Bosch to make ammonia, one of the things that actually makes it easier to run those at large scale is that they can run 24/7 at the exact same rate, at the exact same amount of product I'm making. Which means that running them in that stable, consistent way is something that makes those processes more efficient, actually.
Wait, and that's how they are right now?
That's how
stable.
they run right now.
Okay.
The problem, though, is wind and solar are intermittent. Right? That means that when I use wind and solar to power, whether it's even making hydrogen or directly electrifying these processes, I need to deal with the fact that I'm going to maybe have fluctuations in what my fuel is, the fuel content, or the power content. If I, for example, have a Haber-Bosch plant that I'm going to feed in hydrogen, well, the hydrogen may be produced to some intermittent level. And then if I need to use electricity to power the heat, well, that also may be intermittent if I'm not going to source it from fossil fuel combustion, which means I haven't done anything.
You're not going to run your Fischer-Tropsch plant on batteries.
Exactly. So that's the thing. We're not going to make a bank of batteries just to make our Haber-Bosch plant run its stable operation, right? That's a whole nother infrastructure layer that has to be added to it. So this is why I think things that may seem like drop-in changes still require a lot of innovation around them, right? Yeah.
Is anyone really doing that level of innovation at the sort of integration level, reimagining not parts of processes, but the whole thing and trying to build green facilities that do these things economically as demonstrators?
To my knowledge, relatively little at this stage, right?
I would say there's like trying to make fertilizer, right?
Well,
is that what you're saying? Or trying to make
green
steel?
Plant, yeah.
Well, or imagine trying to make fertilizer in a green way that can operate on an intermittent supply of the energy or the fuel. Because that's what it really would need to be down the line, right? That's a pretty heavy lift.
Yeah, because
right?
One reason is if you have to stop making when the sun sets, your $1 billion plant is sitting there doing nothing for half of the time. And
it's even more than that. A lot of times the catalysts, the things that make the balls go downhill faster, they work the best when they have really pure inputs, really pure outputs, and they're running at the exact same rate all the time.
But is there something in between a completely green plant and the way that we do things now? Is there nothing that's like at 50%? Do you know what I mean? Like where maybe you've altered the chemistry in a way, you don't have to put as much energy into it. But maybe at nighttime it does run on fossil fuels because the sun's not shining. So,
well, I guess I'd point out, solar power and wind aren't the only clean options at our disposal. We have nuclear power.
That's true too.
Which produces both electricity and heat. And I
think
do
so stably.
And very stably. They want to run 24/7. I think one of the really interesting developments in nuclear power that still hasn't really come to market, but will, is the development of small modular reactors that can be sized for industrial campuses like refineries or Fischer-Tropsch plants or Haber-Bosch plants and produce exactly the right amount of heat and exactly the right amount of electricity for a partially electrified process. And I think we're going to see some demonstrations of these things over the next several years as well. Again, in part, thanks to that bipartisan infrastructure law. What is coming to my mind is that, it's so important for us to have a grid. We've talked about the sun setting and rising and the wind not blowing, nuclear power plants, but we have a grid. And the grid does provide a constant source of electricity because we have a diversity of loads and not all on at the same time. And so in electrifying industry, developing that grid and continuing to invest in a diversity of supply and transmission lines that move power around the country and keep the grid stable with a growing percentage of renewable power is extremely important. So electrochemistry and grid development go hand in hand here.
And the other thing I would say that's actually really important to bear in mind is that if you take all the primary electricity needs we have right now, right, and you just take, okay, what's that total amount? And you ask, how much electricity do we need to generate if we're also going to use electricity rather than fossil fuels to decarbonize all this industry? Because that's a significant fraction of the carbon budget, it means we're going to have to generate a lot more electricity from solar and wind. Which means that it's not just a question of upgrading our grid to be able to make it stable with intermittent supply. It also needs to have capacity expansion, right? Because now I have a massive sink of electricity, which is my refinery, which before wasn't that much of a sink of electricity power because it was using fossil fuels to power. Right? So you don't want your Haber-Bosch plant and its desire to run stably to cause intermittency in the energy supply to customers, right? That is another layer that really impacts on how critical it is for our ability to move electricity between places very, very efficiently, right? And our current infrastructure is not by any means ready to tolerate what we would need to get to for industrial decarbonization.
Yeah, and it's worth thinking about what that infrastructure looks like. I mean, we're talking about industrial process electrification here, but at the same time, we're electrifying cars. We're trying to electrify the heating of our homes.
Right.
We're building data centers all over the place that are consuming enormous amounts of electricity. In fact, they're consuming pretty much all of the new renewable electricity we put online.
Well, for a while, we'd kind of seen, the electricity demand level off, and then AI came along, and like all bets were off.
And it's going to get worse. And we're going to produce hydrogen from the grid.
It's huge. I just heard, like, when you do a query for, like, ChatGPT, how much electricity you use, but it's enormous. I think it's like 10 times what a Google search is. It's just, the scale is huge. And when you think about more and more people using that kind of stuff all the time, it's a lot.
So I won't say you can't get there using just solar and wind, but you'll really notice the solar and wind if we're going to increase capacity to that degree. It will be everywhere.
And this is why, and it's a complex analysis. There are certain chemical manufacturers or industrial sectors that may, though there are challenges even with this, have more dedicated off-grid supplies. In other words, like if I build a Haber-Bosch plant of the future, it may make sense for me to have co-located solar and wind I build that's not competing with the grid, but is providing me dedicated power for what I need. But that requires coordinated action to be able to make a grid that is responsive to those future needs. So in a world where there's a lot of decarbonization pressure on industries, but there isn't a grid that allows for that, in a weird way, we're making the less efficient option to take these resources off of the grid and make them be sort of self-serving entities. Right. But that a little speaks to how policy and I think some intentional thought about these things can really, really make a big impact on easing this transition.
And again, a role for government.
A huge role for government.
Really, really important.
Because it's coordination. All these things, because they couple so many sectors, each individual sector making decisions on their own will simply not be able to create the most efficient future of a decarbonized. And every time we make any one of those decisions that's not as efficient as it could be, that means we need to generate even more renewable electricity to meet that inefficiency.
Let's talk about what the future looks like here. Are there countries? Are there companies? Are there venture where is the leadership coming from? Where is this going to happen first?
Wow. That's a great question. When I think about the answer to that question, I think of countries that don't have the luxury of low-cost natural gas that we have in this country and in some other parts of the world that make it really, really hard to displace these fossil-consuming industrial processes. So think about Japan. Japan doesn't have any petroleum to speak of. It doesn't have a very vibrant nuclear sector anymore, thanks to Fukushima. Very, very few options and real pressure to innovate in order to continue to support its industrial sector, I think we'll see things there start to happen. I think in Germany, where there's a very strong green movement, again, no nuclear power or declining nuclear power, but a very, very strong industrial base as well, particularly chemicals. There's huge pressure to see innovation that will bring these processes online first, I think. And I think it's just reflecting on the names of the guys who invented the processes we've been talking about. Right. Those are all Germans. Haber and Bosch and Fischer and Tropsch.
And motivated, actually for the need to generate those things due to war efforts, in the early 20th century, right? That's what really motivated those. Similar issues of stranded capacity, right? But for different reasons, geopolitical reasons. Now, different reasons are motivating that. But I agree that I think that the places where you will see this is where you have, an appetite, political or otherwise appetite for making these investments, right? And also a really need because there isn't a readily available low-cost alternative, right? You think about, some of the pilots have been done in this area, not necessarily in the industrial space, but you think about a place like Hawaii, right? Just the cost of transporting something there means that there are cases where on-site generation and production of certain things makes a lot of sense, right? But and Japan's a great example where, local resources could be tapped to be able to generate some of these things. And that landscape is going to be complicated, and it's going to be also very sector dependent, right? An example you could think of even in a different way, right, is, you have mining operations in remote locations of Australia, right? And would you rather bring in a fuel there or have a dedicated power plant that allows you in a better way to decarbonize that mining operation, right? There are many examples that will be the sort of beachhead places where these things probably will get demonstrated. I think they will get demonstrated, and I mean this in a very sincere way, as they must, with pretty legacy technology. The technologies we're working on in our lab aren't going to be the ones that are obviously are not going to be the ones demonstrated today or next week or next year, right? The ones that are going to be demonstrated in that short time span are the things that we already optimized a lot, 20 years ago or 30 years ago or 50 years ago, right? But the reason we work on that basic science is we would like to give new options when we're 10 or 15 years out that allow us to think about when we need to go to even larger scales. Do we have a larger palette of options that give us the better ability to work with intermittent supply, the better ability to make things at higher efficiency, the better ability to deal with intermittent operation of industrial processes? Those are why we kind of work on those basic sciences to give new options for the future.
So we're going to have, opportunities in different countries that have their own motivations, have different natural resources, have different financial resources. And things are happening. Things are happening in Europe with governments, and the EU is funding a lot of demonstration work. The Japanese are working very hard on things. But there's going to have to be shared learning. So I think there's a real opportunity here for scientific exchange and technical exchange that goes beyond just leaving it to companies to promulgate new good ideas. We really need international cooperation on technology. And there's another practical reason for that as well. If we're talking about making fuels, for example, they're going to go into things like ships and airplanes. You can't have a different fuel in Europe than you have in the United States or South Africa.
You got you're back to your Betamax VHS problem.
Right. And that means that there has to be coordination on policy at a very high level to make all of this stuff work ultimately.
Well, and the piece of fuels is actually a really important piece because, what you're going to actually have in the future is, you may have certain countries because of their renewable energy base and the type of industrial sectors they have that might be really good candidates to produce certain renewable fuels like ammonia or electricity-derived hydrocarbons, for example, right? And those may not be the historical places where we generated those, right? Which means that even like the transport of fuels around the world is going to have to change. That means there's going to be geopolitical consequences to that for sure, right? And then that also means there needs to be coupling between how you best leverage the fuel where it may be used with how it's generated. Like an example is you may, for example, have a really high wind or solar resource that you're going to use to make ammonia in let's take an example in Brazil, and you transport that to Europe, where you're going to cash out that ammonia into hydrogen to power an industrial sector. So then there has to be coupling between those two. And actually, some of the major energy trading companies have actually begun to open desks that trade ammonia because they recognize in the future there are going to be new energy vectors that are going to be used around the world, and that those are going to be traded like commodities, just like we trade commodities of fossil fuels right now.
So give me your best guess, given like the science trends now, the policy trends. When are we going to have plants that produce steel in a better way, that produce fertilizer in the ways that, like, the kind of stuff that has come out of your lab? Is this a 10-year away thing? Is this a
Well, I think, some of these plants exist now.
They exist
I mean,
today,
there are demonstrations. There's a green ammonia plant that was built in the Sinai.
But it's more demo
a couple of years
versus
ago.
like
It's pretty
large
big
amounts.
scale.
Yeah, it is. Okay.
And they're looking at an opportunity. There's a lot of sun that they can use, and there's conventional generation and a reasonable grid. There's a big market for ammonia in Europe that they can easily access with short ship trips and so on. So, you get facilities like that starting to pop up and knowledge being acquired. There is some direct reduction of iron ore. The things are starting to happen. And the question is, how fast can the pace be?
There are demonstrations of those. Like I said, these developments, when they get to scale, they proceed through this iterative process, right? I think the question is not so much because we already have things at reasonable scales. I think that those are going to mature, but at the same time, there are going to be new things that will supplant them, right? And those will start to come online as we progress at the end of this decade and into the next one, right? Okay. And that process will continually get to a point where we reach a level of decarbonization, a high level of decarbonization in these industrial sectors that meets all these other criteria. And that's I think what's fascinating about it, and maybe a little unpredictable about it, is that all the pieces are each moving. The ground is moving in every way around us, right? There's changes to the grid. There's changes to policy. There's also changes to feedstock inputs. There's changes to the regulatory landscape. And that's also coupled with new developments in the technology and new science that's coming up, right? In a way, the fact that everything is moving makes me optimistic, because if only one was and the others weren't, then I would say we should be really worried because we need them to all move together. But the fact that they're all moving together makes me think that this is something that is very tractable on a timescale that's going to matter for climate, but it's going to only matter if we are cognizant of, aware of, and we have both the political will and new of our best and brightest working on the basic science and technical challenges to address these problems.
But they're tractable. I mean, I haven't heard you say once in the course of this discussion, we don't know how to do that, or there's no way to do that, or it can't be done. It's a question of finding the ways, and that's why I feel optimistic as well.
Yogi Surendranath, professor of chemistry at MIT, thanks for being here.
Thank you so much.
What If It Works is a production of the MIT Energy Initiative. If you like the show, please leave us a review or invite a friend to listen. And remember to subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts. You can find an archive of every episode, all of our show notes, and a lot more at energy.mit.edu/podcasts. And you can learn more about the work of the Energy Initiative and the energy transition at energy.mit.edu. Our original podcast artwork is by Zeitler Design. Special thanks to all of the people at Mighty and MIT who make this show possible. I'm Kara Miller.
And I'm Rob Stoner.
Thanks for listening.